This video is going to explain the concept of half-life, and in order to talk about it, we're going to use a really silly example called palladium. So we're going to pretend that palladium is a radioactive isotope that spontaneously decays. And you're already somewhat familiar with this concept of isotopes spontaneously decaying. So let's take a look at our palladium example. So here is our example of radioactive palladium. Every once in a while, this radioactive palladium is going to be cut in half. It's going to spontaneously decay in half. And when that happens, half of it still remains radioactive, but the other half of it decays. So this radioactive palladium sample is now not completely radioactive. Half of it that you can see on the right side has decayed to become stable. So we're going to draw a picture of this and keep track as we go. So before we cut it in half, when we just started, we had this really gigantic ball of Play-Doh. Because it's still the full sample, fraction remaining was 1 out of 1. Everything was still there. So that means percentage remaining was 100%. Before we cut it in half, all of that Play-Doh was still radioactive. We're going to talk about time and mass later. After that first half-life, what we just saw, this sample got cut in half, and half of it decayed to become stable, and half of it remained radioactive. So after this first half-life, we had a much smaller sample remaining. Because our sample was cut in half, then in terms of our remaining radioactive fraction-wise, it's 1/2. And our amount that decayed and is now stable is 1/2. Which means 50% is still remaining. Let's talk about this remaining and decayed a little bit. So when half of our sample decays, it is no longer radioactive. But if it remains, it is still radioactive. Let's watch a few more half-lives to see what will happen. So this is our second half-life. The 50% that's remaining radioactive of that original sample is going to be cut in half again for a second half-life. For each half-life, it gets cut in half. So now our decayed sample has increased and our radioactive sample has decreased. Let's draw a picture of what that looks like. So this sample that we had that was radioactive, it got cut in half. So now we have even a smaller sample remaining. And if we had this half of the original sample that got cut in half again, that means we now only have 1/4 of our original sample, or 25%. So mathematically, we can see that that was divided in half, and that was divided in half. Before we look at the third half-life, make a prediction of what you think will happen in terms of the fraction remaining and the percentage. So here's our third half-life. That 1/4 of the sample that's remaining is going to be cut in half again. Our decayed sample is getting larger, and our radioactive sample is getting smaller, because what we had was just cut in half again. Let's take a look at the fractions you predicted. For this, if we had 1/4 and we cut 1/4 in half, we now have 1/8, which means percentage-wise, we have 12.5% remaining of that original sample. So we can see that every single time we have a half-life, our sample is getting cut in half. Predict the fractions for the fourth and fifth half-life, as well as what size the palladium will be. So for the fourth half-life, we know our sample is getting cut in half again, and it's so small. That was 1/8 of our original sample. And now we only have 1/16 of our original sample that's radioactive. This means if we have 1/8 of our original sample and it gets cut in half again, we now have 1/16 of our original sample. So mathematically, that is 6.25% of that original sample, because every single time we're dividing in half, or dividing by 2, cut in half, cut in half. For our last half-life, for the fifth one, the sample that we had here is going to get cut in half, so we're going to have a very small sample remaining. So fraction-wise, we have 1/32 remaining, which means we have 3.125% still remaining radioactive. So to look at it another way, every single time we have a half-life, we can see that our sample is getting smaller by a half. So when we cut this one in half, this half decayed, but this half moved on. For the next one, this half decayed and that half moved on, and so forth. So our sample is just getting smaller and smaller every single time, which means more and more of our original radioactive sample is becoming stable. Now let's talk about time, because half-life also has to do with time. Our isotope spontaneously decays, but it also decays at regular intervals. So for palladium, our half-life time is going to be 3 seconds. Which means every 3 seconds, our sample is going to get cut in half. So when we first start with our full sample, we'll have time 0. And then after 3 seconds, our first half-life happens. So here's how that works. Our first half-life is 3 seconds, which means when that gets cut in half, it'll go 1, 2, 3. 3 seconds for it to get cut in half. And then only 50% of the original sample is remaining. So there's the 50% that's remaining. And then for our second half-life, now that 50% gets cut in half, 1, 2, 3 seconds, which means our total time that has elapsed would be 6 seconds. So after 6 seconds, we would only have 25% of our sample remaining. And we could keep going and going, and our third half-life would be another 3 seconds. 1, 2, 3, cut in half. And so would the fourth and fifth. So for this time column, let's write the total time that has elapsed. And we know that every single time it will increase by 3 seconds, which means the end of the second half-life, it will have been 6 seconds because we're increasing by 3. It takes another 3 seconds for the next half-life to happen, and now we're at 9 seconds. Another 3 seconds, and we're at 12. Another 3, and now we are at 15 seconds. So we could do something like this then. We could say, well, if the half-life time is 3 seconds, how much is left after 15 seconds? We could say 3.125% is left after 15 seconds. So we can do some calculations with that. And then we could also do it with mass too. So hypothetically, let's say that the mass of that Play-Doh ball, palladium, was 70 grams. After the first half-life, we would only have half of that mass remaining, which means we would only have 35 grams remaining, because every single time we cut it in half. So take a second and see if you can predict what the mass will be at each half-life. Let's check and see how your predictions turned out. So for every single half-life, we divide it in half. So 35 divided by 2, 17.5, divide by 2, divide by 2, divide by 2. And we can do some different calculations with this then. If we didn't have this whole chart filled out, but you knew some of the basic information, like the half-life time and the original mass, we could try to figure out how much mass would be left after a certain time. But we're going to talk more about that in the next lesson. Let's continue talking about half-life conceptually. So the definition for half-life, the time it takes for half of a radioactive sample to decay. So we're going to use this square off to the side and fill out this chart as we go to give us another example of half-life. So at 0 half-lives, 1/1, which means 100% of that is radioactive. Percent decayed and stable would be 0% because all of it is radioactive. So let's say this is our radioactive sample and we're going to show half-lives on it. So after the first half-life, we know that our sample gets cut in half. So this was our first half-life. Fraction remaining radioactive over here is 1/2 or 50%. Now the percent that's decayed and stable is 50%. And that's our first half-life. So for the second half-life, we're gonna take the half that is still radioactive over here and we're gonna cut it in half. It's gonna undergo another half-life. Now, half of this sample decays for the second half-life. And of our original sample, only 1/4 of it is still radioactive. The rest has decayed. So 1/4 is still radioactive. That means 25% radioactive. But now all of this has decayed, which would then be 75% has decayed. Let's keep going another 2 half-lives. So now this sample that is left, that is radioactive right here, gets cut in half again. And half of it decays. So for our third half-life, now 1/8 of the original sample is still radioactive. So that's 12.5%. For the percentage that is now decayed and stable, we need to add up all of these green spaces that have decayed. So we can take 75% and that 12.5 and add it together to figure out how much is now stable. So we have 87.5% is now stable. Let's do the fourth half-life. So half of that sample has now decayed for the fourth half-life, which means only 1/16 of the original sample is still radioactive, which is 6.25%. So another way to think about getting this percentage that's stable, if it's weird to your brain to add those two numbers together, you can think that if 1/16 is radioactive still, then the rest of that has to be stable. So that would be 15 out of 16 pieces would be stable. And so you could divide 15 by 16 as well. And that comes out to 93.75%. And these will just keep going and going and going until we have such a small sample left that's still radioactive that it's really negligible and we have a really stable isotope remaining. You might hear the term parent isotope or daughter isotope. So just a heads up, the parent isotope, that is the one that is radioactive. And the daughter isotope is the one that has decayed and is now stable. So if we're looking at our chart, this would be considered the parent isotope, and this would be considered the daughter isotope. So every time something is still radioactive and it's like your original, that's your parent isotope. And whatever decays, that is now your daughter isotope. The last piece to half-life we are going to talk about is what a half-life graph looks like. And this is a great thing to talk about because sometimes the ACT likes to give you half-life questions, and I've definitely seen these graphs before on the ACT, so a really, really great thing to know what you're looking at here. So for a half-life graph, our x-axis is going to be our number of half-lives, so that's our independent variable. And our dependent variable here is going to be either the percent remaining, or you might see mass remaining as well. For our understanding, we're just going to use percent remaining. Okay, so we have labeled our graph percent remaining and number of half-lives. We're just going to look at about 5 half-lives so that we can get the general idea of what is happening. So to connect this concept to math, we're going to be looking at an exponential decay graph. So you've probably talked about that in algebra at some point in time. But let's go ahead and plot some of these. So we know at 0 half-lives, we still have 100% of our sample remaining. All of it is there. All of it is still radioactive and remaining. But after that first half-life, only 50% of it is still radioactive. We've taken where it was, 100%, and we've divided it in half. For our second half-life, we're going to take that 50% then, and it gets cut in half again. It's now 25%. Same thing for the next half-life. And then the fourth half-life, we have 6.25%, and then it goes down to 3, and it just keeps getting smaller and trailing off down here. So what we're going to do is we're going to connect these dots, but not with a straight line. We're going to use a curved line to show our exponential decay. So because we're just freehanding it, I know that it's not a perfect line, but this is the general shape of graph that you'll see for all half-life graphs. So you're going to see something that swoops down like this and then gets really, really close to that x-axis. So just to recap, you guys now understand that a radioactive isotope will spontaneously decay, and when it does, after a certain amount of time, half of it has now decayed to become stable. So just like palladium, our sample got smaller that was radioactive every single time,